First of all, good afternoon, and thank you for joining us for the California Fire Science Seminar Series. And my name is Ankit Sharma, and I work at NIST and at Johns Hopkins in the US. I'm a member of the student committee who assisted with planning this webinar series, and I will be your host for today. The California Fire Science Seminar Series is organized and supported by the Berkeley Fire Research Group, College of Engineering, University of California, Berkeley, the University of California, Merced, and the California Fire Science Consortium. And before I introduce today's speaker, I'll go over a few housekeeping items. This webinar is being recorded and will be posted on the California Fire Science Consortium website and YouTube channel. All participants will be emailed a link to this recording once it's available, and generally within a week. This email will also include a brief survey, and we hope you will complete it as it helps guide the development of these webinars in the future. So now, without further ado, let me introduce our esteemed guest speaker for today, Dr. Himoto. Dr. Himoto is a senior researcher at the National Institute for Land and Infrastructure Management in Japan. His research interests cover a broad range of fire safety issues in the built environment, and with a special focus on large outdoor fires. With over 20 years of experience, he's an expert in the field of large outdoor fires. He is the developer of various fire computation models, including one of the first physics-based computational models for fire spread in densely built urban areas. His work has been featured and published in different journals, conferences, and media. He is also the author of the popular book on large outdoor fire dynamics, published by CRC Press. And today, Dr. Himoto will delve into the intricacies of physics-based modeling of fire spread in densely built urban areas and some implications to the modeling of fire spread in WUI fires. And following Dr. Himoto's talk, there will be a Q&A session in the end. So please feel free to add your questions in the chat, and we'll try to answer as many as possible in the end. So now please join me in welcoming Dr. Kisoko Himoto.
Thank you very much for nice introduction and inviting me to this seminar. So I would like to start my slide. Okay. So this is the list of topics that I'm going to talk about today. I'm expecting that most of you are outside of Japan. So first of all, I will briefly introduce examples of urban fires that frequently devastated cities of Japan for hundreds of years. This is a picture taken at the city of Kobe in 1995 when an earthquake struck the city. Fire started at multiple locations following the earthquake. Fire spread to adjacent buildings, forming fire plumes above burning structures. This is an example of what I call urban fire. Urban fire can be a general term for all fires that occur in urban areas, but I use this term urban fire as a fire that involves simultaneous burn of multiple buildings in an urban area. Urban fire is not a fire that occurs only in Japan. There are records of urban fires outside of Japan. You have probably learned about the Great Fire of London in history class. Cities in the US were not exempt from such fires. Contemporary cities in Western countries have overcome the issue of urban fires, but cities in Japan still suffer from urban fires, though it is occasional. We can categorize urban fires in three types. They are fires in strong wind conditions, fires following earthquake, and fires caused by aerial bombing in wartime. Historically, urban fires generally occur in strong wind conditions. This is because flames are stretched in the downwind and many burning embers are dispersed in strong wind conditions. But notable damages were caused by urban fires following earthquake in relatively recent cases. An example of fires following earthquake with significant damage is the earthquake that struck Tokyo 100 years ago. Approximately 100 ignitions occurred following an earthquake, since the shaking took place at the time when people were preparing for their lunch. At that time, they used open flames for cooking, which can easily spread to surrounding objects when losing control due to shaking, even for a short period of time. So the fire lasted for 3 days, burning over 200,000 houses and caused over 19,000 fatalities. In this fire case, the most extensive damage was caused at an open space which were formerly used for a clothing manufacturing factory. Huge firewalls were created in the open space with the area of 7 hectares as the fire approached from 3 different sides. About 40,000 people evacuated in this open space at the time the firewalls occurred. About 38,000 people were killed by the firewalls, including those who died after being blown away by the strong wind. Another example is the fires that occurred in 1995 Kobe earthquake disaster. This earthquake itself is recognized as an earthquake disaster with significant human property damages caused by building collapse. However, significant damages were also caused by fires. According to the post-disaster survey, the number of ignition caused in this earthquake was 293. Over 7,000 houses were burned. About one-tenth of all the fatalities were caused by fire. This slide shows the locations of ignition that occurred within 3 days following the main shaking. The blue shaded areas represent the belt of severe shaking with Japan Meteorological Agency seismic scale of 7, which is a maximum. The ignition locations gather in the belt of severe shaking as building collapse in one of the major causes of post-earthquake ignitions. Another example of fires following earthquake is the fires that occurred in the 2011 Tohoku earthquake and tsunami disaster. In this disaster, the damages from tsunamis were significant, whereas the damages from fires were relatively small. But the number of earthquake and tsunami-generated ignitions were as many as 330, as shown in the figure in the right bottom. The number of ignitions was comparative to the one in the 1995 Kobe earthquake, but the ignition locations distributed in a broader range in the 2011 Tohoku earthquake, so the firefighters could respond to these fires except for the heavily damaged areas. This is the reason why fire damages were less significant in this earthquake disaster. One of the features of fires observed in the 2011 Tohoku earthquake is that many tsunami-generated fires occurred offshore. There were various types of fuels involved in tsunami-generated fires. One is the houses destroyed by tsunamis, which is the most common fuel type, as most of detached houses were constructed with wooden members. Second is vehicles. There are several witnesses testifying the start of fire when vehicles collide with each other as they were drifted by the tsunami wave. Third is the burn of vaporized liquid petroleum gas. Most of them were gas cylinders equipped in detached houses. Fourth is the burn of vessels and oil leaked from them, probably exhibited the most frightening scene of the fires in this disaster. In fact, people in Japan were prepared to fires generated by ground shaking, but less to fires generated by tsunamis. So this disaster gave us a warning that attention should be paid to tsunami-generated fires as well. I have mentioned that most of recent urban fires were caused by earthquakes. However, we not entirely free from the threat of urban fires in strong wind conditions. There was a fire in a medium-sized city called Itoigawa in Niigata Prefecture in a windy day in the end of 2016. The fire spread towards the sea and stopped when it reached the coastline. The fire eventually burned over 180 houses. If the city had not been interrupted by the coastline, the fire would have spread further. So we have conducted a post-fire investigation in Itoigawa. We found that most of the buildings in the burnt area were built in 1930s. With low fire safety performance is not in compliance with the present regulations. This is one of the important reasons why fire spread occurred in a long earthquake condition. We have also confirmed that there were at least 15 spotting ignitions caused by firebrands. In the left bottom, we have a picture of firebrands collected in the affected area. You may find that the geometry is somewhat different from those often found in wildland fires, as fire sources are different. This is the latest example of wildland fires in Wajima, which struck the city this January this year. The number of ignitions following this earthquake was reportedly 16 at this moment. This is relatively small for the high seismic intensity of the earthquake. This is because the affected area has a low density of cities with relatively small populations. However, one of the fires that started in Wajima City developed and became an urban fire. The fire burned down approximately 300 buildings in the area of about 50,000 square meters. We have estimated the dynamics of fire spread by analyzing various visual information disseminated by individuals and also the press, as shown in the diagram in the bottom right. According to this diagram, we found that the estimated rate of fire spread was between 20 and 40 meters per hour. This is equivalent to the record of 1995 Kobe earthquake and lower than 2016 Toiga fire. The estimated causes of fire spread has not changed from past fire cases in Wajima fire. One of the major causes is the structural vulnerability of the urban area. This includes the small separation between buildings and low fire protection performance of individual buildings. In addition, buildings were damaged by seismic motion in post-earthquake fire cases, so barewood members of the buildings were exposed outdoors and fragmented pieces were dispersed around the buildings as shown in the pictures. Another factor that affected the behavior of fire spread is the constraint of firefighting activity. In this event, life-saving takes priority over firefighting activity, and the behavior of both local residents and firefighters were affected by tsunami and this warning. Firefighters were unable to take water from the river next to the burnt area due to a drop in the water level following the tsunami. So now I would like to move on to a discussion of the physics-based modeling of fire spread. This part is separated into two parts. The fire spreads in an urban area with and without structural damage on buildings due to seismic motion. So the first model for fire spread in urban area is proposed by Hamada in 1951. At the time this model was developed, there was not enough technical knowledge about fire spread in urban area. However, there was a strong demand for a model in order to design effective countermeasures against urban fires. The model assumes that the fire spread occurs in a homogeneous urban area where buildings of the same geometry are aligned at an identical spacing. The model describes the rate of fire spread from the point of fire origin to a specific direction, such as downwind or upwind, based on empirical formulation from full-scale fire experiments and records of large urban fires. Empirical models are widely used for earthquake loss estimations in various municipalities in Japan. Even today, the figure in the bottom shows the estimated number of burned buildings in one of the anticipated earthquake scenarios. While the use of empirical models is increasing, their limitations are also being recognized. Specifically, the calculation accuracy is low because of the changes in urban conditions since the time when large fires frequently occurred, and the difficulty of validating countermeasures due to the black box nature of the causal relationship of fire spread in empirical models. So we aim to develop a physics-based model for fire spread in urban area. The figure in the bottom shows the schematic of the model. It assumes urban fire as a group of multiple building fires. So the model consists of two submodels, namely the model for fire behavior inside the building and the model for building-to-building fire spread. As for the fire in a building, the concept of the one-layer zone model was adopted, assuming each compartment of the buildings has a control volume of the governing equations. And as for the building-to-building fire spread is considered to take place either by the heat transfer from compartment gas and fire plumes, or spotting ignition by firebrands. Development of fire inside a building from ignition to burnout is predicted by solving the governing equations of fire in each room. This is the basis of the fire spread model. The difference from ordinary one-layer zone models is that the effect of external heating from adjacent to burning buildings is incorporated in these variables. We consider three causes of fire spread between buildings. They are thermal radiation from fire-involved buildings, temperature rise due to wind-blown fire plumes, and spot ignition by scattered firebrands. Under the influence of these causes, occurrence of building-to-building fire spread is judged when either of the three criteria is met. The criteria are the incident heat lags at the opening, surface temperature of building exterior walls, and deposition of firebrands maintaining sufficient thermal energy. One of the difficulties in developing urban fire spread models is to achieve a balance between model accuracy and computational load, given that urban fire is a large-scale phenomena, often involving thousands of buildings at the time. So we employ a simple point source model for radiative heat transfer from window-ejected flame. The point source model assumes uniform intensity in all directions, so the total heat flow through a sphere is constant for all radii. As for the temperature rise due to wind-blown fire plumes, we do not solve the fire-induced airflow in the urban area dynamically, but steady wind profile is assumed in the urban canopy in order to reduce the computational load. Engineering correlations of a fire plume in a quiescent environment is used to evaluate temperature rise in the downwind region. Temperature rise is determined by the heat release rate of the fire source, wind velocity, and positional relationship between the fire source and the heat receiving building. In contrast to the radiative or convective heat transfer models from heat sources, it is not appropriate to take a deterministic approach to the modeling of spotting ignition by firebrands. So we assume log normal distribution in the wind direction and normal distribution in the direction perpendicular to the wind direction for probabilistic evaluation of the position distribution of firebrands. The parameters of the probabilistic distributions were determined based on large eddy simulation of disk-shaped firebrands. The results were generalized using a scale model considering the falling time of a firebrand affected both by drag and gravity. We have actually developed another model based on experiments on firebrand generation and transport, but this is still not incorporated into the fire spread model. So this is an example of fire spread simulation using our model. The target area is a densely built urban area in Kyoto, consisting of about 7,000 buildings. Fire spread basically occurs in a continuous manner, but there are some discontinuous fire spread due to spotting ignition. There are several buildings that remain unburned in the burnt out area. They are reinforced concrete buildings with a relatively high fire protection performance from external heating. Using this fire spread model as a basis, the model was improved to account for structural damage caused by seismic motion. Most of recent urban fires are post-earthquake fires. One of the major features of post-earthquake fires is that fire spread takes place within a group of structurally damaged buildings. So the picture in the left bottom is taken in 1995 in Kobe, whereas the one in the right bottom is taken in 2024 in Wajima. You may find a similarity between these pictures. They are exposure of bare-wood members and disposal of fragmented pieces due to structural damage on buildings. These conditions substantially affect the behavior of fire spread. So the fire spread model was updated with special emphasis on the effect of structural damage on buildings due to seismic motion. The new model assumes that urban area consists of both damaged and undamaged buildings which behave differently when burned. So two burning modes were assumed. When a building materials maintains its integrity, then the burning behavior is modeled using the one layer zone model. So the existing framework is valid. However, when a building is totally collapsed, then combustibles become exposed outdoors. So we employ an engineering correlation obtained from burn experiments of wood crypts for evaluating the flame geometry. Level of structure damage grouped into 5 categories as shown in the table, ranging from no damage to collapse. But prediction of seismic motion and the damage of individual buildings is out of focus of this study. So in our model, the level of structural damage due to seismic motion is assumed to be given as initial condition. The burning mode is determined according to the damage level due to seismic motion as defined in the previous slide. If the damage level is ranked less or equal to major damage, we use the one layer zone model for simulating the fire behavior inside the building. Factors which affect the fire behavior are damage of structure frame, which is represented by the deformation of the building. Crack on walls and windows affect the rate of fresh air supply to the fire-involved room. At the same time, it may become the root of fire spread. The third is falling of exterior materials that reduces the fire-resistant performance of the building. If the damage level is ranked as collapse, then fire behavior and its interaction between adjacent buildings is calculated based on a flame model. Even when the damage level due to seismic motion was ranked less or equal to major damage at the beginning, the damage may be extended due to the heating of fire following the seismic motion. This can cause the shift of the burning mode. As for the damage of structure frame, the result of seismic motion is represented by the tilt angle of one representative column of the building. And the results of heating of fire is represented by the char depth. In order to combine these effects, varying capacity of the column is introduced as the unified index. When the damage represented by these two factors progresses, then the varying capacity of the representative column decreases. When the loading exceeds the decreasing heat bearing capacity, then the failure of the column takes place, leading to collapse of the entire building. This is a failure condition of a column. It is a combined parameter of eccentric loading and force in transverse direction of the column. If the charring progresses, loading position deviates from the center of the column. This will cause deflection of the column, which becomes the maximum at the midsection of the column. The bending moment on the column also becomes the maximum at the midsection of the column. The bending stress at the rim of the column is calculated with last equation, and bending stress by the force in transverse direction of the column is determined in a similar way. Before applying the model to actual urban area, a case study was conducted within a hypothetical urban area where buildings of same geometry were aligned at an identical separation. Pictures at the bottom shows the effect of building collapse upon the behaviors of fire spread. The one on the left-hand side is a result with no building damage, and the one on the right-hand side is a result with damage, with a collapse ratio of 30%. Because the collapse buildings were selected randomly on the right-hand side, the rate of fire spread was asymmetrical. And in this specific case, the rate of fire spread was larger in the damaged urban area. For the model validation, we have analyzed the behavior of fire spread in 1995 Kobe earthquake. This shows the outline of the fire. Fire started from 138 different locations in Kobe City within 3 days following the earthquake. Fires developed from a part of the ignitions, and over 7,000 buildings were burned. Oh, this is the picture of target area. On the left-hand side, we have a picture taken before the fire. We can identify densely built urban areas still remain in the target area. On the right-hand side, we have the same picture with the burnt area overlaid. This is the target area ranging about 2.5 kilometers in the north-south and 2.8 kilometers in the east-west. It is sandwiched between two rivers, sided by the sea in the south. Number of buildings within the urban area was about 25,000. Construction types and geometry of the buildings were obtained from the city planning map of that time. Level of structure damage due to seismic motion for each building was randomly allocated according to the survey data summarized for each administrative area. Red arrows indicate locations of fire ignitions in the target area. There were 17 ignitions. As the initial condition of the fire spread simulation, the time of ignition of each ignition point was given. Most of them started soon after shaking, but some were delayed. So this is a result of the fire spread simulation, lasting for 36 hours following the first ignition. Fire spread was stopped in certain areas where there is wide streets or open spaces. However, wide range area was burnt where there is no effective fire stop. So, the simulated burnt area is overlaid by the record enclosed with orange lines. The simulated burnt areas were comparable in some areas, but they were generally overestimated. I should emphasize that this is a result of one possible scenario. Different result could be obtained if the distribution of the structural damage level of each building was different. So we have performed Monte Carlo simulations with 500 trials to obtain the expected number of buildings burned from each ignition point. Error bars indicate standard deviations. If data point is around the diagonal line, agreement between the simulation and the record is good. Although there were certain variation, the results show reasonable agreement for most ignition points with only one exception, where the number of burnt buildings were overestimated, which is here. One possible possibility of this result is simply the limitation of the model capability. One of the possible reasons is that the effective firefighting activities, which is not incorporated in the present model. Yes, firefighting activity was not incorporated in the present model, so this could have been the cause of this variation. Now we have reached the last topic of this talk. For some implications to widened urban interface fire modeling from the viewpoint of urban fire spread modeling. Urban fires can be classified as outdoor fires, as with forest and wood fires. There are some commonalities of these outdoor fires. Most importantly, it is the mechanism of fire spread. Fire spread in all these outdoor fires is governed by radiative and convective heat transfer from external flame and dispersion of firebrands and burning embers. Such a commonality allows us to adapt a similar approach to the modeling of fire spread. But this is not currently the case, and the model development for these fires is conducted independently. This is because of differences between these fires, which is represented by the combustibility of fuels involved in each fire. However, the distribution of these fuels is more important in predicting the fire spread behavior, because they are equally exposed outdoors. In this perspective, fuels in wildlands are continuously distributed in general, whereas fuels in urban areas are discretely distributed. This could be a cause of fragmentation in the modeling approach between wildland and urban fires. However, fuels in wood have a combined feature of fuels in wildlands and urban areas. So, to my view, extending models for fire spread in urban areas is a promising option for modeling fire spread in wildland urban interface. So a basic version of the fire spread model introduced in my presentation is available on GitHub. So if you are interested, please download and use it. It is an open source code, so you are free to modify it. And the model is written in Python, so it should be easy to work with. It is a little bit early, but this is the conclusion of my presentation. I have introduced the physics-based modeling approach of fire spread in urban areas. This is an engineering model based on knowledge accumulated in the field of fire safety engineering, which were empirical in past days. This enables analysis of large-scale fire phenomena while maintaining a balance between model accuracy and computational cost. Okay, so this is the end of my presentation. Thank you for your attention.
So thank you, Dr. Himoto, for the great talk. It was really very interesting and gave us insights into the modeling of fire spread in the fires. So we'll now open it for the Q&A session. And if you have any questions, please submit to the Q&A box, and we will request Dr. Himoto to please address them. And I think we have received some of the questions. So let's go through the chat box. Okay, so our first question is from Daniel. I think it's more like of a comment, but I will just read it. So comment on the model considering the structural damage due to seismic motion. Might the model also be able to consider structural damage due to strong winds, that is roof covering damage and allowing entry to firebrands? And also, you can see this question on the Q&A session also, if you want to read it again.
Okay, thank you for the comment. Structure damage due to strong wind. So the structure damage due to strong wind assumes that the failure of roofing due to strong wind. In fact, in Japan, the damage on roofing material does not occur that often. In Itoigawa case, the fire spread did occur, but there was no roofing damage when the fire started. So the comment is that suggesting for model improvement for incorporating roofing damage in strong wind condition. Is my understanding correct?
So Daniel, if you are still here and if you want to read your questions or ask questions, so you may please jump in if you want, if you are still here. Okay, I think Daniel is not. Okay, I think he's here. Yeah, please feel free to speak. Yeah. Okay, maybe I think we'll, yeah, if he's not here, we can move to the next question.
Oh,
Or
I
okay.
think I just came off mute. I'm sorry. Can you hear
Okay.
me now?
Yeah, you can hear you. Yeah.
Okay.
Please go.
And I just wanted to say, yeah, I think the comments by the presenter addressed my comment in general that I don't know how to incorporate the wind damage, but I think the insight of applying seismic motion damage to impact the vulnerability of the structure is an interesting one and might also be applied when there is strong wind before the fire. So thank you to the presenter.
Okay, great. So I think now we can move to the next question, and it's by Professor Anand Traue. And I think it's again a first a comment and then a question. So if you want to go through this by yourself, So
Is the commenting on the limitation of the data for model validation, I think.
yes, yeah.
Yes, I agree with this comment that there is a limitation of model validation, but we still have, although very limited, we still have data available for validating model, such as one I introduced in this slides. One of the examples is the case of Kobe earthquake. We have a record of detailed survey following earthquake that describes the dynamics of fire spread in that occurred from each ignition point. So we can compare the dynamics of fire spread following the earthquake. But we also have, we can also obtain data on fire spread from recent urban fires, such as the one in Bajima. So what we can, I do agree with this comment, but what we can do is that we should accumulate data of records for increasing the number of cases that can be validated.
Okay, yeah. Okay, thanks, Ken, for your answer. And I think now we can move to the next question. And I believe it is in Japanese, so I'm not able to read it, but if you can please, so.
The comment from Christy Liu, it says that can the model, does the model incorporate the effect of wind? The answer is yes. We have incorporated the effect of wind, but we assume uniform wind flow in urban area. So we do not simulate fire behavior above burning area dynamically. So this is one of the limitations of the present model.
Okay, and I think we have one more question from the same panel, same participant. So again in Japanese, I think you want to
Actually,
read
this
it?
is the comment is incomplete. So
Okay.
yes, I
Okay,
think
so
I
then we can move
answered
to the
this question. Hi.
next one. Yeah. So next one is from Rasmus, and I think the question is any ideas for using this to detect critical points in cities that would most reduce fire spread if made safer? And how do you get large scale models of a city? Do you manually annotate?
To detect critical point in cities, I think we can use in that way. But the behavior of fire spread changes due to the location of ignition point. So I think what we have to do is perform Monte Carlo simulation, changing the location recognitions to find the critical point probabilistically. This is the approach I can consider for this comment. And related to get large-scale model of city, actually in Japan, digital footprint data is available in every cities in Japan. So I can use that data to construct the model of a city.
Okay, so then I think like due to the time constraints, maybe we can have maybe 1 or 2 more questions. And maybe next question is, could you please comment on the impact of building openings or the size of openings on the phi spread from one building to the other?
The factor of opening geometry is very important in predicting fire spread in this urban fire spread model. It affects the ventilation condition inside a building, and also affect the source of it also behaves as a source of fire, heat source to adjacent buildings. So if the opening geometry, if the opening is large, ventilation becomes active, so the temperature inside the building may decrease. However, on the other hand, as the opening is when the opening is large, then radiation from the burning building becomes increased. So there are two opposite effect that can change the behavior of fire spread in urban areas. So the opening geometry is important in predicting fire spread in urban areas.
Okay, I think and then we can go to the next question. And this is from Charles. And the question is that the physics-based model requires detailed data. So how to work around that? And also, if you have considered firefighting response in your research.
Thank you for the question. Although we can obtain building footprint data in all cities in Japan, we do not have data on openings. As I mentioned, opening data is very important for predicting fire spread in urban areas. But we do have statistical data which was sampled from selected cities that on the ratio of opening area to exterior wall area. So we can estimate the approximate size of openings on each wall, which depends on the separation from adjacent building. So this is my answer to the first question. And the second, my comment to the second question is that we do have model considering firefighting activity in urban fires. I have not included. I have introduced firefighting model in this presentation, but we do have model for firefighting activity, and we have applied our model to the case of Sakata fire in 1976 and have presented it elsewhere. But we have not incorporated the firefighting model in simulating fires following earthquake in Kobe case. but we should have, yes, the fire spread simulation considering firefighting activity should be considered as a future work.
Okay, great. I think now we can have one more question. It's from Edward. And the question is, what assumptions are made in this model about the contents of buildings? And then part two, how would you suggest handling the unknowns of buildings' interiors when using this model?
Does the content mean the fire load or something
Yes, I
else?
think so. The building interior on the loads, fire load.
The fire load is determined based on statistical survey on buildings, which is often used for fire safety design of individual buildings. It depends on the occupancy of buildings. So if the data for occupancy is available, we can estimate the fire load of each building that consists the city area.
Okay, so now we can move on to our next question, and it's by Yerin. So the question is, the physical fire spread model seems to assume ignition inside the structure. Will the fire dynamic change if assuming ignition from outside walls, roofs?
Yes, we do consider ignition of fuels inside the building by receiving heat through windows. But we also consider ignition on exteriors, especially when exterior is made of wood. Yes, incident heat packs at the opening is the first criteria of determining fire spread between buildings. A second is the surface temperature of wooden exterior walls, because fire spread in urban areas in Japan often occurs in wooden densely built urban areas. So this is critical in applying a model to urban areas in Japan.
Yeah,
And
I think due to time constraint, we'll maybe take only one more question. And it's okay. So you gave some details on your spotting transport model. How about the reignition and how do you parameterize it? And same for generation of fire brands.
could you clarify what is reignition means?
I think there is no name, so this question was anonymous. If the participant is still here, so they can clarify by speaking up. Or if not, then we'll move to the next question and maybe the last for today's session. So the question is, yeah, so the question is if the urban forest or green spaces are ever a factor in Japan in terms of increasing fire spread risk in the WUI.
The answer is no. Urban forest is not considered as risk of fire spread in urban areas in Japan because the type of forest in Japan is very much different from those found in US or European countries. Forest fire itself exists in Japan as well, but they were less hazardous or compared to other countries. And especially when they are in urban areas, they are not considered as risk of fire spread. So
Okay. Now I think that due to the time constraints, we have to stop here. So I'm sorry, but don't worry. Like if your question is not answered, we have taken a note of all the questions and we'll email all these questions to Dr. Himoto, and answers will be shared with the survey email to all the participants. So as we wrap up for today's session, I want to thank you for joining us and also thank all the members of the committee for organizing these series. Special thanks to Dr. Himoto for the great talk. And remember, our next session is scheduled for February 20th with our next speaker, Dr. Ali Mogmi, where he will be discussing AI-enabled wildfire detection using satellite imagery. And before we sign off, please keep an eye out for the webinar evaluation that will be shared or emailed this week. So thank you once again, and we look forward to seeing you all in our future sessions. Have a great day.